Hello, everyone. Oh, Oscar, do you need a little bit of time? Okay, I'll just get started then. So today is about Ethereum smart contracts, and we're going to talk about use cases too. So very exciting. And then I have a few slides to kind of like help you set up a mental model on how to look at use cases. So let's say there's an ICO you want to invest in. You can read the paper and see if it's a good use case, whether or not you should put your money into it. There's a lot of other reasons why an ICO might be a bad idea, but you can look into like why we may or may not want to use blockchain for a certain use case. So first off, like, who here has heard of Ethereum? Cool, a lot of hands. Who feels like they know what Ethereum is, have a good grasp of it, can maybe explain it to me? Ooh. Yeah.
Ethereum is considered like a supercomputer in a way.
Uh-huh.
It's like a virtual machine that makes use of the blockchain to store smart contracts, which I kind of see it as like the new back end of an application. That's totally transparent and that's mobile and nothing can change. And it allows for peer-to-peer apps or
Okay, yeah, I really like it. It kind of harnesses the powers of blockchain. It does smart contracts, and it kind of can enable a lot of cool things in the future that we get from blockchain. So cool. We're going to talk more about the actual definition, or however we want you to think about it. So here's kind of what we're going to go through today. But before we really get into Ethereum, I want to ask a question. What makes Bitcoin so special? Like, we spent the last month or so talking about all the things that it does, but like, why are we so excited about it? Why is so much money being poured into it? Anyone have an answer for me? Why are you sitting in this class? Why do you care? Yeah?
that people could create money without a centralized authority.
Mm-hmm.
Nobody ever thought that anything like that could ever have been possible.
Yeah.
But it was like money that was created
Mm-hmm.
in the community.
Yeah. Mm-hmm. Yeah, I like that. No centralized authority. Any other answers? Maybe about the cool things that were introduced when Bitcoin was introduced? Starts with a B, rhymes with blockchain. No? All right. Okay. So I kind of have my own answer to this. This is just my personal opinion. So Bitcoin is just special because, like you said, there's no centralized authority. It's a distributed network, and we don't need one person controlling it. And the way we do this is like the cool part, right? We have cryptographic identities instead of identities tied to personal information. So this still allows us to transact with someone consistently on the network and trust that it's the same person every time. We can have signatures that prove that they sent the transactions, stuff like that. Then we have the really cool thing that we call blockchain, which is the data structure that allows us to have this immutability, right? It's append only. Once something's been committed to it, we can't change it anymore. And we all store the same information on the blockchain, and we each have a copy. And because we're equally invested in what the information actually is, we actually all have equal say in agreeing on what kind of data goes into this blockchain. And that brings us to our trustless consensus protocol, right? So instead of having one person make the decision for us or some kind of authority, we all come together and come to consensus. So that's pretty cool. So what we get with this distributed network is pseudonymity, or you could even extend that to anonymity if you want. I'm not saying the word right. Anonymity. And that is really cool, right? You can preserve your privacy. It's democratic. So for the first time, we're making decisions without a central authority. It's immutable, and most importantly, because nobody controls it, it cannot be censored. It cannot be brought down easily. There's no central point of failure, right? So I really like this meme, the government banning Bitcoin. I try to incorporate as many memes as I can into this class, so if you like that, thumbs up. All right. Oh, by the way, forgot to mention this. We actually posted the worksheet, the discussion worksheet on Piazza this time. So if you want to go to Piazza right now, you can pull it up. And while you're following along with lecture, see if you can answer the questions that are on that worksheet. And if you can, that means you're on the right track and you're getting everything that I'm saying. All right. So maybe I'll give you like 10 seconds if you want to pull it up. All right. So, smart contracts. So the definition of a contract is just a written or spoken agreement that is intended to be enforceable by law. Usually there's like two parties, and the whole idea is I'll do this if you do that. And we kind of rely on the government or the police or lawyers or whatever to kind of put the muscle behind this agreement so that it cannot be broken. That's the whole idea, is once we've entered into a contract, the whole point is that it's going to happen. There's no breaking it. But of course, you know, we have lawyers and all that in case that does happen. So the idea is, why don't we take this smart contract, this sort of trust that we're putting into the other person to fulfill their end of the agreement, into code? So why don't we have the code just execute and make this contract fulfill itself? Right? Because when we run code, like the code doesn't decide like, oh, I'm feeling lazy today. Oh, I accidentally spent my money, so now I went bankrupt. Like the code doesn't have the same flaws that a human has. So we think that we can trust a code to always give us the right answer and always do the thing that we want them to do. But obviously the caveat here is it's not decentralized yet. When we say smart contract, we haven't actually stepped into the decentralized world yet. It's just that we're putting this into code, an executable agreement that will run the same way every time. So we need a trusted entity to run this code. So why don't we take the logic behind needing a trusted entity to make decisions for us and bridge that over to a trusted entity running smart contracts for us. Does anyone have questions on smart contracts first? Okay, cool. So Ethereum. This is Ethereum landing page. The whole point of Ethereum is it's a decentralized platform to run smart contracts. So what was your name?
Mark.
Mark. What Mark said before was we are using the whole idea of a distributed system, this trustless system to run smart contracts. So instead of having a centralized entity run the smart contract for us and we trust that their output is correct, we have a decentralized, everybody runs the code and we come to consensus on exactly what the output was. So we have a distributed computer in that sense. And I'll go into this later, of course. And we have a distributed state machine. So in Bitcoin, we have a state. And the state would be who has what amount of money in their accounts, or how many UTXOs they have, basically. But in Ethereum, this state can be like how much money you have, what are the values in these variables, who has ownership over these things that are not maybe coins, and many other things as well. So when you send transactions in Ethereum, you can change more than just the account balance in someone's address. And also Ethereum is a cryptocurrency. You can 100% call it a cryptocurrency. It has a native asset called Ether, and it's traded very regularly. Who here actually has Ether? Cool, yeah. Making money? Losing money? All right. So a little bit of background. We had Bitcoin, first successful cryptocurrency. It has been tested over the last 10 years. It hasn't been hacked successfully. Its trust is immutable, uncensorable, pseudonymous, whatever, no central point of failure. And we said, like, oh, like, why don't we put smart contracts on this, right? And that's exactly what Vitalik, Buddha, and this guy said. But the thing is, the Bitcoin community is very, let's just say, like, vanilla would be their favorite flavor of ice cream. And they're very resistant to change. So they very much like their gold standard Bitcoin protocol, and it's very hard to implement like crazy things like, oh, let's make this a smart contract platform. Things have been built on top of it, but it's very hard to actually propose like a software change within Bitcoin. So if you remember, we said there's BIPs. In order for a BIP to get passed, we need like a certain majority of the network to all agree, yeah, I'm gonna upgrade my software on this day. So it's very difficult for this to happen. So what Vitalik did was like, all right, I'll make my own thing. And that's how we have Ethereum. So let's compare and contrast Ethereum and Bitcoin for a second. Like I said, Bitcoin is considered the gold standard of blockchains. It is the vanilla flavor. It's the most basic one. It's very simple, very robust, and because it doesn't do very many things, not very many things can go wrong. And so, like I said, over 10 years, it's been tried and tested and has been working. So people trust Bitcoin a lot. But like I said in 2 lectures ago, it's not very complex. Like I said, it's not Turing complete, so there's not much you can do with the stack-based program language. Script is very, very basic. Whereas Ethereum is a smart contract platform. So you can say that both are cryptocurrencies, but the point of Bitcoin is to transact a currency, and the point of Ethereum is to run smart contracts. That, I would say, is the most major difference between the two. And while Ethereum has a asset, Ether, it is mostly used to fund computation, reward miners, and align incentives. So I'll go into more of how you can use Ether for things like gas later, but the main point of Ethereum is not that it's a transaction system. And Ethereum actually has a Turing-complete scripting language. It's complex and feature-rich, and that's what allows you to make smart contracts on it. Another difference between the two is, yes? So Turing-complete, you can think of it as being able to, so there's this definition, it's like you can have different conditional statements, so you can have ifs and loops, and then you can like change different parts of memory. There's a lot of, like, there's a more thorough definition of Turing completeness, but it's kind of a theoretical concept on how we can classify languages and their capabilities. Yeah. So just think of it this way, like you can do a lot more with Turing complete languages. Yeah. And then one other difference between them, Bitcoin is UTXO based. We all remember the UTXO model very well, I hope. And Ethereum actually uses accounts, and I'll go over why. Bitcoin uses proof of work, and it probably will always use proof of work because, like I said, hesitant to change. And Ethereum is in the process of kind of blending in proof of stake and switching to Casper. All right. A few implementation details. Ethereum's block time is actually around 12 seconds, so things are being updated more quickly, and that makes sense because when we're running smart contracts, we don't want to wait 10 minutes for something to go through. And its cryptographic hash function is ETHash, yes, yeah, ETHash, which is currently ASIC resistant or considered ASIC resistant instead of SHA-256. Its exchange rate, I just updated this over the weekend. It was like 230 bucks, so pretty strong. All right, so accounts. In Ethereum, we actually use accounts. And this, the most basic reason is that when you're coding smart contracts, it's much easier to say balance of this person instead of add up all the UTXOs and see how much money they have, right? It's just easier to code. And you actually have 2 different types of accounts. Externally owned accounts would be like you or me or my mom or my dad or maybe UC Berkeley or whatever entity is creating their own account on Ethereum. They would have their private and public key, and they would have an address as well as Ether balance. So this is just the most basic version of account, who it belongs to and how much money is in it. Then we have contracts. So smart contracts will actually have their own accounts, and they have a little more than just their address and their balance. They also have their internal state, so the variables that they're storing, the different memory that they have. So that can change constantly with different transactions and functions being called within the smart contract. We're clear on the 2 different types? Okay. So I have a question for you. I kind of want to do more like clicker questions. Obviously, there's no clickers, but I'm going to have you guys just talk amongst yourselves, and then we're just going to take a poll with raising our hands. Don't be afraid to have the wrong answer. It's all about what you come up with. And these are kind of more open-ended questions. So my first question is, what are the strengths of the UTXO model? And the other question is, what are the weaknesses of the UTXO model? So we know like Bitcoin is pretty cool. There were reasons why they chose this like not super intuitive UTXO model, but like why did they do it? What are the pros and cons? Can you guys talk amongst yourselves for maybe like 60 seconds and then I'll take a poll. Okay, so what's the best way to do this? Do we want to cover our eyes to make sure like we're voting honestly, or let's just keep our eyes open? So who thinks that verifying transaction validity and checking double spending is something that UTXO's model is really good at. Cool. All right, that's the right answer. All right, there's actually more than one answer, of course. Who thinks that the UTXO model is very space efficient? All right. Okay. So I would argue against that actually, because storing a list of UTXOs is taking up more space than just a balance. Just a balance. What? Okay, Dave, can you please explain? Yeah, I think is nuanced. All right. All right. Okay. Okay. So there's nuance behind it. And who thinks that looking up account balances quickly is something that the UTXO model is really good at? Okay. Okay, Dave. Okay. And who thinks that ease in programming is something that the UTXO model is good at? All right. So this is the one that I kind of wanted to discuss. So when we were programming in Bitcoin, our main concern was double spending. So it's very easy to say like, take this UTXO, check if it's spent or not, and then spend it if it hasn't been spent. But of course, when we are coding smart contracts, like I said before, we're interested in just quickly saying like, look at the account balance of this one. Obviously, it's like very nuanced, but you can think about it that way. All right, so I kind of have some explanations for everything. Bitcoin, main purpose, prevent double spending. Ethereum, the slide says it's space efficient to update balances instead of storing UTXOs. Obviously, we store things differently in Ethereum, and it's not just as simple as just saying this is the balance. But for the purpose of just, thinking about the two models, we'll do it this way. And it's also easier to look up a balance and transfer between accounts when you're programming in Ethereum to just say, check the balance here, send it to the other balance and update it. Okay. So how to think about smart contracts in Ethereum. You can think of them as like autonomous agents. Like maybe you can think of them with like eyes and a mouth and hands and legs and whatever. And they live inside the Ethereum network. Once you've uploaded it to the blockchain, it lives forever, and then you kind of like poke it with transactions. So let's say there's a very basic smart contract that holds everyone's balances and can send between accounts. So then I would call a function in that smart contract, say like send money that, information in yours, send money from my account to Mark's account. And then it'll say like, oh, I just got a transaction, I got called, and then it'll execute the function and then transfer the money to basically transfer the data that they have in their thing. So they have direct control over their internal Ether balance, and they have direct control over their internal contract state. So let's say this contract actually doesn't have Ether in it, but has like boba tokens. So I'm buying boba from like Daniel or something, and I'm like, all right, in this smart contract, I'm gonna say send 2 boba tokens from my account to Daniel's account. And this smart contract, its internal state says, oh, each person has this many boba tokens. And this is not Ether, right? This is boba tokens. And let's say there's a function that says I can cash out my boba tokens for Ether. Then this smart contract's Ether balance will be used in like sending me that Ether, or I'm sending them Ether, whatever it is. So that's what I mean by internal Ether balance and contract state. I just wanted to use that example to make it super clear. Is it super clear? Any questions? Yes. Sorry? Okay, so when you say explain it all again, go back to slide 1. Okay, so let's say this guy is a smart contract, and he handles, or I just assumed his gender, whatever. We're gonna say that his pronouns are he and him. Okay, and he is like the boba token smart contract. So what he does is he handles the transfer of boba tokens. So he maybe internally he has like a table of like my name and Daniel's, everyone in this room's name to a number of boba tokens. That makes sense? Maybe it could be like a hash map or a table, whatever it is, right? And then so I say like, oh, I want to buy boba tokens, and these boba tokens are going to allow me to buy boba in Berkeley. So what I do is I send that smart contract ether with a message that says I want to buy these many boba tokens from you. And so in that smart contract, it's going to have a function that takes in like my message and then can change its table and update like, oh, I just received some ether. So now my ether balance is higher. And also I want to give Gloria like 5 boba tokens or whatever it is, right? And then I go to like Daniel's boba shop and I say like, I want to buy boba from you. And he's like, all right, that'll be 1 boba token, right? And then so I then send another message to this same smart contract that says transfer between Gloria and Daniel, 1 boba token. And then so because this smart contract has control over its internal state, right, it can say like, oh, okay, I'm going to update the table so that Gloria has 1 less boba token and Daniel has 1 extra one, right? And then let's say Daniel's like business is like booming, and he wants to he wants to spend this money. So he wants to cash out his boba tokens into ether, and then he's gonna convert it to USD or whatever it is. He just wants to take money out of this contract. So he will send the smart contract a message that says, I want to cash out my boba tokens. And then what the smart contract will do is like, oh, I got another call. So I'm going to go through the function that cashes out his boba tokens. So I subtract all the boba tokens from this value in the table. And then I will then change my ether balance so that I'm sending it to Daniel. And in Ethereum, like that's how transactions work. Obviously, is like you can send ether from one person to another. Is that explanation that was okay? It was followable. Okay. Another question. Mm-hmm. Mm-hmm. Yes. It is within the block. Yes. So blocks will record changes in the Ethereum network state. And that state includes how many ether that each account has, the values of different variables, etc. Yeah. So that table that I mentioned would be updated, and that would show in the block. Yeah. Okay. Yeah.
The blockchain is storing like account balances versus like transactions.
Yes.
And Bitcoin is just transactions.
Well, okay, you're storing transactions as well as account balances. Yeah. So the way that it stores those transactions is different from Bitcoin. I'm not going to go into it because it's technical. But yeah, you can think of it that way. Mm-hmm. Yes, exactly. Yeah, it won't show up as like you're not going to look up your address in Ether and it be like, oh, this many Ether, this many boba token. That's all handled by the smart contract. Yeah. Yes. Yeah. But that smart contract wouldn't just disappear, right? Yeah. Okay. Another question. Yes. So you will code your smart contract and push it onto the blockchain. This code is available for anyone to see, of course. And then, yeah, like someone coded it, but after that, you cannot go into the smart contract and say like, oh, because I wrote this smart contract, I get to decide how much each person has. It lives by itself. And you can update it, of course, but you don't own it, if that makes sense. Any other questions? Yes. Mm-hmm. Okay. Oh, how would you update the smart contract? Or, I actually don't know exactly how it works. But I think you would have to like, oh, Dave, you want to answer that?
So contracts on the encoder have optional order field. So the order field sets and you can make updates. If there's an order field that's never be
literally update code, but you can trace kind of like a cross sequence. So you just use the new address. Yeah. Or you can use the
Okay, let's go to the next slide. So Ethereum smart contracts generally serve four purposes. So the first would just be to store and maintain data. So you could theoretically just have a smart contract that like stores names for you, and then you can just send a message that says, "Oh, add this name to your data." And there's other examples too. Manage contract or relationship between untrusting users. So let's say there was a smart contract where you could implement escrow. So it's like, I want to buy a house from Daniel, or like whatever. I want to buy his boba shop, whatever it is, right? So I put my money in the smart contract, and then the smart contract will hold that money in escrow and not send it to Daniel until it's sure that the deal has been done and he's transferred ownership to me and all of the loose ends have been tied. Then the money then goes to him. And then if Daniel does something sketchy, then it will find out and then it will send the money back to me. So it's kind of like mitigating that risk and being the third party for us. It can also provide functions to other contracts. So there are smart contract software libraries that will do like various arithmetic functions for you, so you don't have to write your own. Generally, you could write your own if you want to make sure that it's secure, but if you trust another smart contract's implementation of something, then you can then call another smart contract. So smart contracts can also call each other within Ethereum. Or complex authentication. So we talked about multi-sig in Bitcoin. Obviously, you can still do that with Ethereum, and it's actually easier. All right. So here is a simple betting contract written by Nick, who taught our developer decal, and this is a betting contract. So if we want to go through line by line, the first is the public owner, so that would be the owner of the smart contract, like Dave said, and then you have two addresses, or three actually. You have the two gamblers as well as the oracle, and the oracle is going to be responsible for telling the smart contract the outcome of the event, because these two people are going to be betting on an outcome. Let's say like whether or not Daniel's boba shop is going to go bankrupt, something like that, right? And then you have a bet. You can make a bet on the outcome that you think is going to happen, how much money you want to put into this bet, and whether or not it's initialized. And then we have, okay, addresses to bets. So every time you put in a bet, this smart contract is going to keep track like, oh, Gloria made this bet. So very simple. And then winnings. So after the bet has been finalized and we know what the outcome is, then this mapping will be created where it says Gloria lost, so she gets 0 money. Daniel's boba shop didn't actually go bankrupt, so that means he gets the money. However it is. And then so other functions. So let's say this is actually where the transactions come in on Ethereum. So let's say I want to do a transaction to this smart contract. So I'm going to make a bet. And I'm going to say I want to bet this much money on, whatever happening. And then the function make decision is we have assigned a specific oracle, like a third party that can be trusted to make this decision for us, like the government, or what if you don't trust the government, some random dude. And they are going to be the oracle, and then when the outcome has happened, they will then call the smart contract and say, this is what happened, this is the outcome. And once that decision has been made, the smart contract is going to be like, oh, okay, now I know the outcome. Now I can calculate who won how much money. And then we have withdraw. So let's say in the end, Daniel's like, haha, I won. He can then call the smart contract and withdraw the amount of ether that he won because he won this bet. So we can see how code is understandable. Yeah? We all feel good? All right. Yes?
Does the oracle have to be like an institution, or can it be like an event happening?
Right.
The decision of.
Right. So oracles is like a big topic because it's kind of a source of centralization, right? Because you need someone to make the decision for you. So in this case, it specifies the oracle to be an address. So in real life, what you could do is have like a whole like voting system attached to this, where people like vote on what the outcome is, and then all that data is then like scraped, and then like you have like this address like then inputting it into the smart contract. you can have hardware oracles, for example, like a RFID scanner scanning like a barcode, and then that will automatically like transmit it onto the blockchain and make this transaction for you. There's various ways that this oracleization can happen. Yeah. Does that make sense? Okay. Okay. So, the next step is, okay, we have these smart contracts. Now, how does mining and validation of these contracts work in Ethereum? So I just took the recipe for mining from Bitcoin and just added an extra step to it. So obviously the miner still has to download the entire blockchain, they have to verify incoming transactions, but on top of those transactions, they have to run the smart contract code that those transactions call, right? So when I say like I want to make a bet with this smart contract, there's code that needs to be executed on top of just me sending money to this contract. So the miner would be responsible for this. Then they create the block, just like in Bitcoin, and then they also have to do the proof of work, so they find the valid knots. And so just think of it as basically the same block. Obviously, there's different information in it, and it's more complicated than just transaction data. But they still have to have this block. They hash it, and they keep hashing it with the different knots, like the process that we mentioned last week, until they find the valid proof of work answer to this hash puzzle. And then once they've found a valid block, then they broadcast it onto the network, and hopefully it gets accepted by the network. This makes sense. It's a very easy jump from Bitcoin to Ethereum. Okay. And of course, they profit from it. All right. So you can think of Ethereum as a distributed computer. So the whole point is if we had one person run the smart contract, and we could trust that one person, like sure, this would work. If the government created a smart contract platform for us, maybe in the US, we would actually trust for it to work properly. But you know, in cases where we don't trust the government or whoever is running the smart contract, we want a distributed computer. So just like in Bitcoin, we have all of these nodes, not every single node, but a bunch of nodes in the network, validating these transactions and running the smart contract code to get the new network state. And just like in proof of work, someone who wins this race is going to be proposing the next block. And it's a competitive process, of course, so only one person's block actually gets updated onto the blockchain. And this removes the need for a trusted third party to run the code for us. So we get why Ethereum is important in the smart contract process. Like we understand why we have Ethereum. Do we? Yes? Okay. I saw one person nod, so I'm feeling good. All right. And with Ethereum, because you have this immutable, transparent blockchain, these secure peer-to-peer agreements live on the blockchain forever. And everyone can see it, and everyone knows that it happened. Yeah. Okay. So any questions? Yes, Mark.
So one thing I'm thinking about is how every node in the Ethereum network needs to run the smart contract code.
Mm-hmm.
But at the same time, the miners run the smart contract code. And they're trying to calculate max.
Mm-hmm.
So if I execute a contract, a smart contract,
Mm-hmm.
does every single node in Ethereum, aka the miner, have to solve the
Execute
problem
all the,
and then
yeah.
execute the contract code
Well,
every single node?
execute the code and then find the puzzle
Every single node.
every time. Well, I mean, you can choose whether or not you participate in the process, but yeah, every node does it. All right, question. Yes. So we will talk about proof of stake 2 lectures from now, or actually I think next lecture we'll mention it too. If you want, if everybody wants, we can go over Ethereum's specifically, but it's a little bit outside of the scope of this lecture, so I'm going to ask you to hold on to that question. Is that okay? Okay. I saw another question, Devin. Or not Devin. It's just an arbitrary decision to have it be updating faster. Yeah, yeah. So like I said, the proof of work puzzle in Bitcoin is set to a certain difficulty so that it only happens every 10 minutes. but Ethereum is different.
It's just the level of difference.
Yeah, it's kind of just a knob that you're turning. Yeah. Okay.
There's two types. There is the knob. The fear is most of the time to be too small. You have issues where like some miners will have it really small.
Mhm.
They just keep mining the whole thing, which causes issues. So there's a protocol update that was published a few years ago called Ghost, where Ethereum has you include the fail blocks hackers in there as well. So Ethereum does that, which lets you safely go in time limit.
Yeah. So the shorter your time limit is, the more forks you have. So Ethereum has a way of trying to minimize that by including like cousin or like nephew blocks or uncle blocks. That's what they're called, uncle blocks. Okay, I saw a couple other questions. No more questions? Yeah.
Is there like a difference between how miners are incentivized with Ethereum as to or against Bitcoin?
A difference? I guess the difference would be like you're rewarded with Ether instead of Bitcoin, but otherwise the scheme is pretty similar. Yeah, it's pretty similar. Yeah. Yes.
Is it safe to assume
Yeah, that's safe to assume. Yeah. Yeah, so I'll get into that very soon. So the answer to that is gas. So just wait a couple slides. All right, any other questions before I move on? Mm-hmm.
Just the output of the content stream if you like validates it. Everything's determined by that person through like the mining process.
Yes.
So like
Yes.
in the end state around like the output of the content, like how is that being like validated? Like if the content is like doing that.
So you're asking how to decide whether or not the contract output is correct
Yeah.
by that one person? Yeah, so just like in Bitcoin, if someone uploads a block with transactions that you don't agree with, you can choose not to accept that block. And so similarly in Ethereum, if someone's smart contract output produces a result that you don't agree with, you can choose not to accept that block. Now, of course, if everyone in the network says like, I don't want to accept that block, then that block will be ignored. But usually the block will be accepted by everyone in the network because if you are another node that tried to validate these transactions and you came out with an output for this code and it's very different from someone else's output, maybe you would decide not to accept that. And if everyone around you also sees that, then that is just going to be ignored. So I guess it's the answer to your question is we can choose whether or not to accept the block. But whoever wins the proof of work mining puzzle is going to have like first pick on like what the block is, right? Does that answer your question?
Just to complement a little bit, it's back in you committing to a rule and you're like posting it out there. Like before that happens, after the whole process guarantees that you're committing to a rule and you're posting it in an immutable thing. So you cannot like back up. So it's not a person doing the validation, it's like the rules you committed to, the contract, it's just like sticking. Maybe that.
Yeah, and the next thing that I'm going to go into is the Ethereum virtual machine, which kind of ensures that everyone will get the same output. Yeah. So any last questions before I move on? Okay, I'm going to move on. Okay, so Ethereum virtual machine. Now, the cool part about Ethereum is not really just that it has smart contracts or that it's distributed. It actually, because this Ethereum virtual machine exists, we have all these cool functionality. So I'll explain what that means. The Ethereum virtual machine is basically just like a compiler. Well, you compile it and then you run it on the Ethereum virtual machine. So we've written all these like smart contract code in Solidity, and then soon it'll be Viper. It's compiled into EVM code. So if you've taken 61C, this is very similar to when you compile your C into assembly language. And this EVM code is like easy for a machine to understand. It's like line by line instructions, whereas we have this human readable version and human codable version, and now we encode it into something that the machine can do. And then everyone on the Ethereum network has their own EVM. So it's kind of like a mini computer, like a virtual mini computer that you will download onto your computer. And this EVM is actually what runs the smart contract code. And because we have taken all this like Turing complete goodness that we can write smart contracts in and compiled it into this EVM code, then after we run it on this EVM, which is going to control this environment that we're running the code in, and it's uniform across the network. So every time you run the same EVM code on the EVM, it's going to have the same exact output. So there's no such thing as like I have a different computer from you, or I like switch the settings on my computer so that it has a different result. Everyone runs it on the EVM. So that's why if someone runs it on the EVM, then we can usually trust that that is the correct output. Does that make sense? Okay. All right, so there is an issue when we have Turing completeness, right? We can write loops. And because we have this distributed computer, everyone is running whatever smart contract that we wrote. So let's say I'm a malicious adversary and I say, all right, I want to launch a denial of service attack. And so I write a smart contract that has an infinite loop in it. And I submit a transaction to the network that calls this function. So then everyone running this function is going to be stuck in an infinite loop. Do we understand why everyone will be stuck in this infinite loop? We understand because everyone's running it, right? And so this is really bad for the network because if you're forcing like many computers to just do nothing but be stuck in this infinite loop, right? And if you've taken CS70, you'll know that by the halting problem, we actually cannot look at a piece of code and determine whether or not it's going to be stuck in an infinite loop. We cannot see if it's going to halt or not. So there's no solution to deciding whether or not to run code based on what it is. So we have to basically stop this loop from happening. So how do we do this? Well, the answer is gas. So every contract requires gas, which fuels contract execution. So in EVM code, we have different opcodes. So each instruction has some kind of operation done to it. And each one of those opcodes is going to take a certain amount of gas. So let's say you are adding two things together. Maybe that takes a little bit of gas. Let's say you're calculating a cryptographic hash function. That might take a little bit more gas. And obviously, if you're in a loop, every iteration of the loop you're going to have to pay for gas for. And the reason behind this is you're paying for this distributed computer, basically, to run a smart contract for you that's going to give you a trustworthy output. So you should have to pay for that. And so when you are transacting, you're going to know what smart contract your transaction is going to call. And so what you're going to do is specify a start gas, which is how much money or how much gas you're willing to pay for in order for this transaction to go through. And also a gas price, which converts that gas into Ether. So Ether is how we transact on the Ethereum network, and that's what you're going to use to pay for your transaction to go through. Yes, questions? I guess it's just a design choice. The prices of gas can change over time, as well as the price of Ether. So what I'm guessing is that the amount of gas that each opcode takes is like constant. So the amount of gas is not going to change, but the value of Ether will. So that exchange rate is going to change, but you're not going to have to pay like 10 times more for the transaction to go through just because Ether's price went up 10 times. Does that make sense? Yeah. All right. Another question. Because you're not running smart contracts. Yeah. So earlier you had a question about what is Turing completeness. So when something is not Turing complete, you cannot write a loop. Yeah. Yeah, so there's no loops in Bitcoin. Yeah. Yes. Yes, exactly. So if you want to have the analogy in Bitcoin, because you're only sending transactions, so there's transaction fees. So that would be the equivalent of gas. Yeah. Cool. Yes. It is awarded to the miner of the block. Yeah, so you are paying the person who ran your smart contract for the running of their code, of your code. Yeah. Any other questions? I have a couple more slides, so maybe if you have a question, it'll get answered. So at the start of the transaction, you have your start gas multiplied by your gas price to get the amount of ether, basically, that you are willing to pay for the smart contract execution. And so if it successfully executes, you might have some gas left over, and that's going to be refunded back to the person who sent the transaction. And this makes sense, right? Yeah. And then if the execution runs out of gas before it executes completely, it's actually going to terminate, and it is not refunded back to the sender. And now this would kind of suck if you accidentally forgot to put enough gas. But the whole idea is we want to prevent these infinite loops from happening. So the idea is if you are looking to launch that denial of service attack that I mentioned, and you want to call an infinite loop, it wouldn't make sense for you to be refunded back your money because it didn't execute completely. We want to penalize the idea of these attacks happening. So you will not get refunded if it doesn't execute all the way. That makes sense? So I just want to kind of reiterate again, when you pay for gas, you pay for your smart contract being executed, or a smart contract being executed in this distributed computer. It's not free, and I don't think it should be free, because you're paying for this like trustworthy outcome of the code. And the more complicated your smart contract is, or the more complex actions that need to be completed for your transaction to go through, the more gas you should have to pay. And gas fees are not very expensive. It's like very, very little money. But we still have this in place to prevent attacks like I mentioned. Are there any questions about this? Yes. Yes. So, yes, yes. Yeah, so like storing information would be another opcode in the EVM. So a store with more information, like storing a byte versus a word or whatever it is, the bigger amount of information you're storing, the more you'd have to pay. Yeah. Yes. Okay. Yeah, so theoretically, if everyone was stuck in an infinite loop, that would be denial of service because the network cannot function anymore because everyone's occupied doing this stupid loop. But the whole idea here is, let's go over this example again. So I write a smart contract with an infinite loop in it. While true, do this, right? And then I call that smart contract and I tell everyone, hey, like, run my transaction that goes into this infinite loop, right? And I have to specify amount of gas that I'm willing to pay for it. So what they're going to do is they're going to do a start gas, they're going to go into this infinite loop, and then if I put in a lot of money into it, like sure, it'll take them a while to come out of the loop, but I'm not going to get my money back. So it's going to achieve nothing. I guess we could force the network to be stuck for a few seconds or something, but it's not worth it because you lose all that ether. Yeah, so we're disincentivizing this type of attack. So are you suggesting that maybe while you have kind of frozen the network, you can submit whatever transactions you want?
Yeah, I'm wondering if you shut down the whole thing,
There's no incentive. I mean, the whole idea of like a denial of service is like this network sucks because it's easy to hack into, or not hack, but like it's easy to just launch this attack.
There was incidents for the whole movie. They actually stayed on the off the advertisement and
Mm. Yes. Mark.
So theoretically, if I'm a user of that,
Mm-hmm.
decentralized that, I find smart contract, and I want to make sure that a transaction is successfully executed, I kind of have to guess how much gas it's going to cost. So I have to be smart about that, right?
Yes, yes. There are resources online where you can guesstimate how much gas your transaction is going to take. So, I mean, the safest option would just be to put in a lot of gas, and then it will be refunded back to you if it's not used. But yeah, that is correct. You would have to kind of guess how much gas you need. The miner would get the gas. So when you put in gas, the person who runs your smart contract, aka the miner, is going to get the gas that is used, and you are going to get the gas that is not used refunded back to you. Yes.
Maybe I missed that, but in terms of how are the contracts, which contracts are chosen to be sort of processed next? I remember from a big part of it was for block access and different
Mm-hmm,
sort of get priority
mm-hmm.
in terms of what's happening. How does it work differently?
Right. So, for example, you could specify that you're going to pay a higher price of ether per unit gas. So that would be like a higher transaction fee, and someone who is wanting to earn more money would then be like, oh yeah, I want to run this one before. Yeah.
That's a really simple, really.
Yeah.
Because if I go out there and I say I'm putting a certain price,
Mm-hmm.
and then can I change that or iterate that, or is it sort of how static or dynamic is that?
Right. So you can change your gas price whenever you want. Yeah. That's specified at the start of your transaction. Yeah. All right. Good question. Any other questions? Yes, please. Yeah. Um, I can see why you would argue that it's a big problem. But from what has happened, I don't think it's posed any problems in the past. Like I can see how you mean, like, oh, you can kind of control, what happens because you can pay more for what you want. But I think it's just a prioritization of which transactions happen first, which is so far like not a big deal. Yeah, I'll look more into that though. It's a good question. Yeah. Mm. What?
So let's say I want to execute a transaction and I guess too low. That's
Mm-hmm.
the price. Then what you're saying is the execution runs out of gas if it hurts.
Mm-hmm.
Do I lose the money?
Yeah.
And
Yep.
I lose it. So
Yes.
I can't ever guess too low. I lose my money.
Yeah. All right. Yes. Theoretically, yes. Right, so each opcode is going to require a certain amount of gas, and then your gas price specifies how much ether you're going to pay per gas. So the higher your gas price is, the more you're going to pay for the same execution. Yeah. Mm-hmm. Okay, good questions. Any other ones? Yeah. Yeah. So that's what I mean by like you guess, but like there's ways of calculating it. So it's pretty unlikely that you're gonna accidentally guess too low. Yeah. Yeah, like I'm sure there's a table online where you can search up the opcode to the amount of gas that it takes, and then you can just calculate it. Okay. They get the mining reward. Yeah. Oh, no, no, no. I don't know how much the mining reward is. I can look it up for you. Yeah. Okay.
How big is the communication now?
Putting me on the spot. I mean, I don't know. Alexa, like.
I mean, as it gets larger, like mainstream, would it be an issue that it gets like ever more centralized because people cannot hold
Yeah, that's definitely a problem for all blockchains. Yeah. I mean, I just went to like this cool meetup yesterday that talked about sharding. So maybe in the future you could just store a subset of the information on the blockchain, and different subsets could store different ones. So in that case, you'd be able to split the blockchain into pieces, and then not everyone has to store everything. Yeah, I like don't quote me on that. Like I don't know if sharding is like a good idea or not. But you know, yeah, I haven't looked into it too much, but theoretically, yeah. Yes.
So what is sharding? Sharding is one of the main core components for scaling.
Mm-hmm.
So I just wanted to make that's conceptually the same. And if you're just making a few more timelines, like at the moment, the last time I can see something
Yeah. Yeah. Yeah, like I don't know exactly like the implementation details or like how well figured out it is, but it's something to look forward to in the future. Just Ethereum. Yeah. Okay, I'm gonna move on. So I have a clicker question. Test your knowledge. So recall that gas is used to pay for your smart contract to be validated by this distributed computer. Remember, it's a distributed computer, so everyone runs this. But how much gas do you need to supply? Enough for one person to run the code, for everyone to run the code, just the delegated validators to run the code? What would your answer be? So maybe talk amongst yourselves, get like a good answer, and then I'll poll. Do we have an answer? Are you ready? You got an answer? Okay, who thinks that you only need to give enough gas for one person to run the code? Alright, Alright, I'm curious now. Enough gas for everyone to run the code? Enough gas for just the delegated validators. Alright. Alright. So, you're going to broadcast this transaction to everyone you know. And hopefully everyone's going to hear about this transaction. Then when the transaction is validated, everyone's going to try to validate it because while they're creating the block, they want to include your transaction. So everyone's going to run this code. And everyone's going to take this gas. So, let's say everyone comes up with a block. How many blocks are actually added to the blockchain? Just one. Yeah. So, the blockchain has one block. And I said that the person who validates your transaction is going to get rewarded your gas. If this process is competitive and only one person is able to add their block to the blockchain, how many people get rewarded according to this blockchain? One. Good job. So I included this question because Someone asked me this question once, and I was like, wait, but everyone's running it. Do we need enough for everyone? But it's a competitive process. Only one person's block is added to the blockchain. So we all understand why? If you don't get it, raise your hand. If you get it, raise your hand. Okay, is there a question? Mm-hmm. So you're asking how we would run out of gas, given that only one person is going to collect it? Mm-hmm. Yeah, so everyone, yeah, so basically everyone else doesn't get paid, right? And it's the same thing in Bitcoin. You can mine all day and never get the mining reward, right? It's the same thing here where you could be running all these smart contracts constantly, but you never get paid for it. But the idea is that you hopefully will get one block where you do get paid. No, you don't. No one need to pay for one person. Mm-hmm. 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 Oh. So you're asking if like every time someone runs it, they take out gas, and then another person runs it and they take out gas. Is that what you're saying? No. So everyone's gonna run this separately in their own EVM, in their own environment, so it's not affected by someone else running the code. Yeah. Yeah. Everyone has their own computer. Yeah. Good question.
So say in the case that someone wrote a smart contract and like what's the step-by-step process? Like, so the right infinitely one runs that infinity program, and then once they once the gas provided is more than the competition, less than the competition provided after, then they all decide to give in.
Yeah. Yeah. Separately.
Then in that case, oh, okay.
Yeah. Okay. Another question. So the smart contract would not change any of the Ethereum state, but the gas would still be rewarded to the miner, to the person who ran the contract. There would be other things in it, but yeah, that would not be.
The idea, I guess, is to punish or like for you to have to pay a currency amount of money, you prevent how much load you're going to have. So that's why if your thing fails, it's still compute. Like when you broadcast it, so you try to do it well. It's still run the computation, so you're paying for actually try, even though it's not actually paying the same. That's the idea.
So who gets the gas money if it fell because no block is being recorded? So which miner is going to get a gas money?
It's in the other transaction is still included in the block, and so whoever closed that block still gets the gas.
Yeah, the transaction is included, but it doesn't change any of the network state. Yeah. So it tried, but it didn't work. Yeah. Okay. I'm just gonna move on. So here we have the state of Ethereum, and it includes how much ether people have, what the data is being stored, everything. And you're going to message this transaction, and it's not just going to include the inputs and the outputs and how much money. It's also going to include things like gas, things like changes you want to the memory, stock PC, whatever it is. And then it's going to change, and we get a new block state and a new amount of gas. That makes sense? Cool. All right. So one thing that I want to mention is Ethereum is not about optimizing efficiency of computation. If we wanted to run code efficiently, we would do it on one computer, not a bunch of them. It's redundantly parallel, meaning that you're doing the same thing on a bunch of different computers. And that means that it is expensive, it is slow, it is memory intensive, because everyone is storing all of the data, everyone is running all of the transactions, everyone has to pay for maintaining their own node. It's not supposed to be efficient. It's supposed to be a way for us to reach consensus amongst all of our parties and have a trustworthy output of the code. So, given that, we're going to look at a lot of use cases. And you're going to see a lot of use cases as you're in the blockchain space. You're going to see like different consulting companies that are big names. They're all about like, they earn so much money because they're so smart about management, consulting, and strategy. But they're going to come up with all these really bad use cases, and you're going to be able to tell, yeah, this is a bad use case. So I just want to ask you guys, like, how would you decide while you're reading a paper like this, like whether or not it's good for a centralized solution or a decentralized solution? What are some things that you would look for? Some questions you might ask.
Do the two firms not trust each other?
Exactly. Do they trust each other? Because if they trust each other, then they can just use a centralized database. Like we can share data by just having our own thing, right? Any other things that you might consider? Yes. Does it need the extra security? Exactly. Another one. Does it need to be private? Mm-hmm. So if it had to be private, all right. Does it need to be fast, right? Because I just mentioned that it's like not very efficient to run code on Ethereum. I saw another hand. Yeah. Does it need to be flexible? I've never thought about that one, but yeah, okay. Yes. Okay. Yeah, because the more calculations, the more we would have to have everyone do it, right? Any other ones? Yeah. Sorry? Fault tolerance, yeah. So that's actually on my slide. All right. Any other ones? These are really good. All right, next one. So this is kind of just a slide that I put together. This is not like verified or certified or whatever. This is just kind of what I use. So personally, when I look at blockchains, my first thing is, do we need a shared database, right? If we're not sharing data, if we don't need to deal with data, why are we using blockchain, right? And if people trust each other, there's no need for decentralization because we can have a trusted authority do everything for us. So the trust thing is a really big thing. If we want fault tolerance, data immutability, or censorship resistance, like let's say we want to do something that nobody can control, blockchain's perfect for that, right? But if you see, the other side is a lot longer because there are a lot of cons to using blockchain, and there are good use cases for it, but there's a lot of bad use cases for it too. So when would you use a centralized database? If it doesn't need to be shared, if it doesn't need to be data, if parties trust each other, there's no point, right? If you want to keep it confidential, most blockchains are public, right? So if you're going to have a public ledger of something, you can't be storing like your confidential data on there. Likewise, there's no such thing as we're going to put this giant PDF on the blockchain and have everyone store it. Bad idea. Of course, you could have a centralized source of data and then have it encrypted or something, and then do some kind of like access to the data being transacted on the blockchain. But don't put like textbooks and like, all that's like, don't put large or complex pieces of data on a blockchain. It's just not scalable. If you need to be able to edit things that happened in the past, you can't do that in a blockchain. So don't look in there. And if you're interested in efficiency or cost effectiveness, unfortunately, blockchain's not super good for that. But if you're weighing the pros and the cons and you find that the pros are more than the cons, then definitely make an educated decision about this. So I guess this would be like the big money slide from this presentation. All right, any questions on that? This kind of marks the end of all the Ethereum stuff that I'm going to talk about, and we're going to jump into use cases. So if you want, I can just jump right into use cases and then post all your questions on Piazza. All right, I'm going to move on. no break. All right, use cases. All right, so first of all, basic use cases. A token system implementation. So in the beginning of the class, I mentioned Boba Coin. Yeah, that's kind of the idea. You have a token, and this is kind of like if you wanted to make Bitcoin on Ethereum, you could do it in these 4 lines. Obviously, if you wanted to make it more secure and whatnot, you would want to use more than 4 lines. But this right here is how you would do Bitcoin or Boba Coin. Yeah. All right. Public registry. So let's say I wanted to map domain names to IP addresses, so we could keep track of which domain names are already taken. So maybe Jillian Chu maps to 1, 2, 3, 4, 5, 6, 7, 8. And then, so all we have to do then is keep a register of the name and the value. Every time we want to add a new thing to the register, we check that if it's already taken or not. If it's not, great, we can add it. And this is all on the blockchain. So this registry is publicly available to everyone. It's not mutable. So we have this like transparent, immutable record, which is the whole point of blockchain, right? And you can keep track of whatever you want this way. So proof of existence. So you could prove that you own some kind of document. It could just be a hash of a document. So you don't have to store like the whole thing on the blockchain. And there would be timestamps later. So let's say I want to say that I wrote this book. And I wrote it today. And then so what I'm going to do is I'm going to hash the full PDF of my book or whatever it is, and then put that hash on the Ethereum blockchain, and let's say it's in like this registry, for example, and it maps from my address to this hash document. So in the future, I can prove, first of all, that I made this document today, because there's going to be a timestamp on that block when it was published, and I can also prove the original version. So if someone then comes out with a book with like all these like really bad things that are like libelous or like illegal or whatever, and they say like, oh yeah, Gloria wrote this, I can say like, no, because here I'm gonna hash the original one and it matches. Yours doesn't match, right? So we can prove the integrity and the existence of different documents. So pretty cool use case, very basic. Last, I want to say March, Brian and Jillian, our other 2 lecturers, as well as another person in blockchain at Berkeley, went to ETH Denver, and they hacked up this smart contract that basically incentivizes people to do things. So for example, on Stack Overflow, you could put a bounty on a question that you have, that you're wondering about, and then someone who answers that question can then be rewarded with Ethereum. So very interesting. They used MetaMask to integrate it to the front end. I wasn't the one who made this, so I don't know all the technical details, but you can ask Brian or Jillian. Yeah. So the idea is I have this question, and the prize for answering it would be this much. And it runs through a smart contract. All right. Any questions on the basic use cases? The ones that can be coded in a couple lines? Okay. Advanced use cases. So decentralized land titles. So like I said, this is kind of just a one step up from the public registry. The idea is in some countries, you cannot always rely on the government to back you up when you say that you own this piece of land. In some cases, the government might actually come in and say like, well, this is not your land anymore, this is mine, right? So we cannot always trust our central authority, aka our government, to keep an accurate record or make decisions for us. There's bribes, there's tampering, there's all kinds of things that you don't want to mess with. So the idea is we can take these land titles, represent them in some shape or form on the blockchain, and people can then have ownership over these things. So you could have a public registry that maps a person or an address or whatever to a certain land title. Or you could trade the land titles like tokens. So, like I want to transfer it over to you, and it would be as easy as sending a certain amount of tokens. Yeah. And there are countries that have implemented this. Last time I checked, Georgia and Sweden were kind of like leading the charge on this, and they're actually implementing hundreds of thousands of land titles on a blockchain, which is pretty cool. Okay, any comments or questions? Land titles? Uh-huh. So the idea then is whatever it says on the blockchain is the truth. It's like public and transparent and immutable. Obviously, you're hitting on something that is a very big problem. Let's say someone who is not trustworthy is inputting all this data into the blockchain. So then you're putting bad data into the blockchain and it's still bad data. Blockchain doesn't like actually know anything about the data that you're putting in. So yeah, if you have a faulty land title, then it's still going to be faulty even though it's on blockchain. Yeah, exactly, exactly. Yeah, so one solution to your to your thing that you mentioned would be the government is trustworthy today or something, right? We just don't trust them in the future. So today the government uploads all this land title information into the blockchain, and then everyone sees it, and everyone's like, yeah, I'm cool with this. I'm cool with this. Cool. And then it's like immutable from now on. So that could be a solution, but of course, that inflow of data is really what we want to control. Yeah. Yes. Within Ethereum. I mean, you can make as many accounts as you want, just like in Bitcoin. Um, yeah, yeah, you can make as many as you want. Does that answer your question? I don't know. Yeah. Yeah, so the idea, you would call that an oracle, yeah. Someone who inputs into the blockchain. Yeah. Okay. Do we want to hear more use cases? Right. Okay. So this is a pretty cool idea, prediction markets. So you draw on the wisdom of the crowd to a certain event that is going to happen at a certain time in the future. So for example, who will win the 2020 presidential election? That's something that can be easily verified and is going to have a due date or a time that the event ends. And so basically what you have is bets. You can think of that just like a bet. And you are putting money in, and those are shares to the particular outcome of this event. So the idea is like, let's say we're selling Zuckerberg shares and we're selling Trump shares. If people in general think that Zuckerberg is going to win, then it's going to be more expensive to buy these Zuckerberg shares because it's more likely that the Zuckerberg shares will pay out. Because if Zuckerberg wins, then the Trump coins are worth nothing, and the Zuckerberg coins are worth, all of the money that was put in. So obviously, in this case, you also need oracles to decide like who won the presidential election. Something like an election is like very easy to have an oracle for because, like, it's like a publicly verifiable event that everyone knows. There's however many hundreds of millions of people in America that can attest to whatever the outcome is. But there are other events that are maybe harder to report on. So this is particularly good for a decentralized case because, well, there's no restrictions on what kind of market you can create. So the government might say, in a regular betting environment, there's restrictions on like what's legal and what's okay to put on a prediction market. It's like sometimes a good thing, but the idea here is there's no censorship. And we have a shared liquidity pool, and you can eliminate the middleman that takes a cut out of the betting. So if we just have a smart contract, the smart contract doesn't need to be paid, so all the money can then go to winnings. And it's automatic and it's trustless, so we don't have to trust someone who's taking all of the bets to actually pay out, because it's just going to happen automatically when the smart contract is executed. So we understand why decentralization is good for this use case. Yes, okay. So some implications of this use case. So for example, you could buy information such as, will this movie be a flop? So let's say I'm doing marketing for the next, I was about to say Harry Potter movie, but there's no more Harry Potter movies. Oh, whatever, like the next Marvel movie, yeah. It's like, will this be a flop? And I want to kind of gauge what the public feels about this movie. So I then put it on a prediction market, and people can put money into whether or not they think it's a good thing. And then based on whether or not the movie is a flop, then people will then earn money. So basically, I'm like paying for market information, which is a good use case. Some other use cases would be like hedging and insurance. So let's say Daniel's Boba Shop again. He's building on like in Berkeley, and there's like the San Andreas Fault like right next to us. So he's gonna say, I bet that my boba shop is going to be destroyed by an earthquake that's going to happen before 2020. And so in 2020, the outcome of this event can be decided whether or not Daniel's boba shop was knocked down by an earthquake. And an oracle will decide that for us. And so he puts that on, and he buys a bunch of shares that says it will be knocked down. And then I am like, nah, earthquake hasn't happened in so many years, it's not going to happen. So then I buy up all the shares that say it's not going to get knocked down by an earthquake. Well, this is kind of like an insurance policy, because Daniel is paying a little bit of money to basically insure his boba shop. So basically what happens is, if an earthquake were to hypothetically knock down his boba shop, then all of my money goes to Daniel, because he won the bet. He gets money. And then he can use that money to pay for all of the losses that he incurred because of this earthquake. So it's kind of like an insurance policy. Obviously, if his boba shop does not get knocked down, then he just paid this amount of money for his like insurance. It's like a premium. Right, so it's a pretty good use case. Security bug bounty. So let's say I am a software company, and obviously I invest a lot of money into the security, but there's always a chance that some hacker is going to expose some kind of vulnerability. But my hope is that someone will be like a white hat and just tell me about it in a nice way, so instead of like coming in and taking all of my money. So then I can put a bug bounty that says, okay, this smart contract says, if you reveal a vulnerability in my security system to me in a white hat manner, then this money will go to you. And this incentivizes a hacker to be good to me and basically not maliciously just take over because of a vulnerability that they found. So that's another way, kind of like an insurance, but like, bounty. And then ICO signaling. So you can write a smart contract that says, I want money, or so let's say I have an ICO, and I say, I am going to deliver my products on time. And I bet, in this prediction market, I bet that it's going to happen by next Tuesday, or like 6 months from now. Okay, let's say it's going to happen 6 months from now. And then other people are like, nah, like, I call you a bullshit, right? So I'm going to buy shares that say you're not going to deliver. And then so in that case, so if I do deliver, then I get their money, and I can spend that money on whatever it is that I'm working on in my ICO. But if I don't deliver, then all that money goes to them, because like I wasn't honest. Yeah. Is there a question? Mm-hmm. Yeah. Okay. Yeah. So in real life, you would have like different clauses in a contract. So similarly, in this smart contract, you could write different clauses that say, if my house burns down and it wasn't me that did it, and it wasn't my friend that did it, blah blah blah, then whatever. You can make it as complex as you want. But the idea is like it's still like a verifiable yes or no question at the end. Yeah. Mm-hmm. Another question. Yeah, so that was my next slide. So let's say I bet $1 million that Brian will be alive tomorrow. So the next person can say, all right, $1 million. Well, I bet $1 million that Brian's gonna be dead tomorrow. Then he goes and kills Brian, and he wins the $1 million from me. So basically, what you could have said all along was I was basically setting up an assassination market, right? So whoever I want dead, I can just say, I bet they're gonna be alive tomorrow. Someone's gonna kill them for me, and all I had to do was put it on a prediction market, right? So this is why prediction markets are illegal. um, in most cases. But yeah, there's always this thing with technology is you can do a lot of cool things, but you can also do a lot of bad things. Yeah. Are there any questions? Very good question. Yes.
Those the same problems exist with like regular money.
Yeah. Yeah, you could argue that, right? Like, I don't need blockchain to set up an assassination market, so blockchain is not any worse than regular. So we should allow blockchain. Yeah. Yeah. Cool. No questions. All right. So this is like the big money, arguably the most popular use case that every company wants to work on, supply chain. So the idea is we can track our supply chain information through this immutable, public, transparent, wonderful ledger. And for businesses, we could set up smart contracts so that transfer of ownership between different stopping points in the supply chain can be automated. Maybe we can just have secure hardware oracles that are automatically scanning all of our RFID tags on our products, and then the smart contract automatically executes, and then we don't have to worry about any kind of intermediaries taking a cut. So it sounds like this amazing thing. And then for consumers, see, I'm already coughing. For consumers, it's like I can look up this product on the blockchain, and it has this transparent, immutable public record, and I can check, for example, is this fair trade? Were the workers fairly compensated? Did they create? I can then look at the place where it comes from and see if it's like sustainable. I can look at if it's ethical. I can see if it's organic. It's like a very, very nice way to certify goods. I can see whether or not it's counterfeit. So let's say my Louis Vuitton purse has a whole history on the blockchain, and I can see that the Louis Vuitton company actually verifiably authenticated this purse. Or let's say my drugs, my prescription drugs, have a history on the blockchain, and it's not counterfeit because I know that it went through all these secure processes. It's a very wonderful, wonderful idea. So I try to put as many means as I want. So like we mentioned before, we need to trust the data that is inputted into the blockchain. What you can do is take this counterfeit drug, or take this like real drug, replace it with a counterfeit drug, and then it goes through the rest of the supply chain, still pretending that it's the same drug. Let's say there's like secure RFID tags on these Louis Vuitton purses. I just take this Louis Vuitton purse, rip it out, make 10 copies of it, or 100 copies, 1,000 copies, and then I put them on fake purses and I put them back in the blockchain, right? You're gonna end up with transparent, immutable, trustworthy, whatever it is, garbage in your blockchain. So basically what we're doing is delegating the trust to the endpoints. We can trust that whatever data is in the blockchain is like integrous, it's immutable, whatever, all those adjectives that we use all the time, and you always hear the businesses saying it. It's in all of the different consulting companies' papers. All of the supply chain use cases are going to use all these words, but they never address the fact that we need to make sure that the data that goes into the blockchain is good. So I like to use this example. We call it the grape problem. Because let's say I am going to use this for sustainable agriculture, and I also want to show that my fruits are organic, and all of my workers were compensated. So I set up this amazing, amazing, amazing infrastructure where I am certified by like all of the governmental organizations. I set up my supply chain, and all of the people who are going to take my grapes and sell them on the market. And what I'm going to do is I'm going to use RFID tags, like encrypted, like expensive RFID tags that are like sure to never be corrupted. Once they're touched by like anything, it'll upload directly onto the blockchain. It can track the temperature, the location, whatever, right? And I'm like, all right, I'm going to use these on my grapes. The next question is, do I put it on every bunch of grapes? Do I put it on the subvines? Do I put it on each individual grape? Like, how do I decide where to put these RFID tags, right? So the whole point of what I just said is it's very, very hard to reliably bridge the physical world with the digital world. And that's a huge problem that I'm really interested in solving, but I really don't have an answer to it. But it's a big problem. All right. Yeah. Because they're not thinking about this big problem. Yeah.
Isn't this problem going back to what I said about money?
Mhm.
Doesn't this problem also exist with
Exactly. Yeah.
so like you're already
Yeah.
operating
Yeah, yeah. It's just that people are saying like blockchain can solve this problem, but it can't. Yeah. All right. So there is one supply chain use case that I really like, and it concerns blood diamonds. So every diamond has a very unique crystal structure. So this is an example of where a physical item actually has a unique identifier that you can then upload onto the blockchain. So you could take this structure and maybe use it as a way to generate the private key or whatever ID that you're using for this diamond. And then you can reliably track each diamond uniquely between the physical and the digital world. So I really like this particular use case because I think it solves a problem. Yeah, it's a cool one. Another one is smart energy grids. So let's say we have a situation where house A has all this extra heat or extra energy, and house C is like lacking. So how do we set up some infrastructure between house A and house C so that we can more efficiently transmit this energy? Now, obviously, like, we're not gonna go to like PG&E and be like, hey, can you like set this up for me? This would be an example of some kind of community project that we want people to pool together money for and then set up, execute on whatever action that we want done. So what we can do is set up an Ethereum smart contract for financial commitments. So you say, it's kind of like a Kickstarter where it's like, oh, we're all going to pull in our money, and then if it happens, then the person who executed on it is going to get all of our money. If it never happens, then we still get to keep our money. So that's just another use case. Any questions? I think there's a couple more. Oh, there isn't. That was the last one. Okay. So blockchain versus the internet. Yeah.
It doesn't send you money.
That is a very good use case. So the idea is right now if I want to, I mean, my mom is doing this right now where her parents sold a house in China and now they live in the US. But for them to send all of that, however many $1 million it is, to the US, they would have to go through all these hurdles and pay taxes and pay transaction fees, and they would lose like a really big chunk of that money. So what they can do is like, but the idea is that if you just put it all in Bitcoin or in some kind of cryptocurrency, you could send it and kind of go through all of those borders and barriers without actually having to go through them, and then you just take it back out, and it's kind of like a little tunnel that you went through that allowed you to subvert all of this stuff. And the idea is like all this like different banks, like Ripple does this, where different banks can transact with one another, different international banks, different, like across border payments, basically. Yeah, I didn't include that because I don't know. All right. So the last thing I want to talk about is just like blockchain versus the internet. When the internet first came out, people were like, what is this? Like, this is stupid. Nobody's going to ever use it for anything, right? Like, there's no use case. The internet is stupid. And now look where we are today. So blockchain just came out, and that took about like 20 years, something like that, 20, 30 years. Blockchain came out in 2008. Today is 2018. So if you ever, hear people out there saying like blockchain is stupid, there's all these problems, the stupid grapes problem will never be solved, have hope, like me. Blockchain will work. Just give it some time. So this is your homework for the weekend.